Okay, this is the second video for section 15.6, which is about triple integrals. And let's remember the stuff we did in the previous video. That's, so to speak, type 1, but you don't really have to memorize which one is type 1, type 2, and so on. But anyhow, the point is this. Triple integral is given in this way, where the solid E is a three-dimensional solid, some object in three-dimensional XYZ space, like this one. And if it's given by some region bounded by Z is equal to U1, which is a surface, and then Z is equal to U2, which is another surface, namely it's a region sandwiched by those two surfaces. And in this case, the idea is you first fix X and Y and integrate with Z. And then for each fixed X and Y inside this region, your Z value changes from the bottom surface to the top surface. That's why you integrate from U1 to U2 with respect to the variable Z. And then once you carry out this integration, the variable Z disappears, and what you're left with is only X and Y. And then what you get is double integral, like this double integral. And then the region of the double integral is, so to speak, the shadow of E on the xy plane. Namely, you just light up this solid directly from the above, vertically like this. And then the shadow of this, namely what you get by projecting this down on the xy plane, is the region D. That's the region you double integrate, whatever you are left with after you carry out this integration. So that's the idea of triple integral. And of course, you can actually generalize you have a different situation for E. Namely, there's a situation where you fix Y and Z and integrate with X, or you fix X and Z and then integrate with Y. And those are respectively called type 2 and type 3. So type 2 is the situation where you fix Y and Z and integrate. Integrate with X. And this is used when the solid you integrate is sandwiched by two surfaces. Both of them are solved for X, namely X. And then situation like this. And then suppose this portion is X is equal to U2 YZ. And then this one is X is equal to U1 YZ. And then this one D is the shadow of E. Or to be more precise, it's called a projection. The precise mathematical terminology is projection of E onto the YZ plane. Essentially, what this means is shadow. This is, by the way, shadow is not shadow. Sorry, shadow. It's not really a mathematical terminology. This is just my terminology. But anyhow, D is just the shadow you get by lighting up this solid from this direction. And then in this case, the solid you integrate over is written in this way. Triple integral dv is written as double integral over this shadow, and then you first integrate this with x, and x is from u1 xy and u2 xy and dA. So the idea is you fix y and z, and for each fixed y and z, your x value varies from u1 to u2 like this, and that's this integral. And then after that, you double integrate whatever you are left with over the shadow. So that's another scenario. That's type 2 scenario. And then finally, type 3 scenario is when you fix x and z and integrate with y. So this is used when your solid looks like this. So this is a shadow, this is D, and then the bottom surface is y is equal to u1 xy xz, sorry, and then this one is y is equal to u2 xz xz, and then for this case, and this is our E, and for this case, the triple integral dv is written as you first integrate with a y, and then y is from here to here. Limits for y is u1 to u2, and u1, u2 are in terms of x and z. So the idea is for each fixed x and z, namely on xz plane, your y value varies from here to here. So that's why we get this. And then we double integrate whatever you are left with over the shadow of this solid when you light this up from this direction, vertically to the y-axis, and the shadow would be like this. Okay, so let's work out lots of examples. For the rest of this section in this video, pretty much what I'm going to do is to work out a bunch of examples. And then usually in a problem, it's not given that which one to use. Use type 1, use type 2, type 3, or whatever. Usually it's not given. You have to find out which variable you take care of first by looking at the problem. For example, evaluate triple integral 2x dx, oops, dv, where our E is by using set notation xyz such that y is between 0 and 1, x is between 0 and root 4 minus y squared, and then z is between 0 and y. Okay, then now which one should we use? Well, in this case, basically, the idea is you have to fix two variables and you integrate with the other one. So you have to pick up the variable you integrate first. And in this case, one way to figure out which one to take care of first is to look at the set notation if it's given in this set notation. And in this case, y is between 0 and 1, but now x is between 0 and some surface. And also z is given in this way. And indeed, one way to tell which one is the best one is to basically look at the variable which appears in the least complicated way. Okay, the least complicated variable is the variable you should integrate first. That's the basic rule of thumb. So once again, look at the set notation, look at those, and which variable is the least complicated one. Well, if you look at y appears once, twice, and 3 times, and moreover, it appears in like square root of 4 minus y squared. So y is the most complicated guy. Okay, y is the most complicated guy is y. And then on the other hand, x appears only once here, and z appears only once here. So in this case, in principle, it doesn't matter which one to take care of first. So let's integrate with x first, namely fix y and z, and integrate with x. With x. So this is, so to speak, type 2. But like I said, you don't have to memorize which one is type 1, which one is type 2, and so on. Just to figure out which variable you integrate first for each problem. So in this case, triple integral over e of 2x dv. This is written as d. We're going to figure out d later, so let's don't worry about d for now. And then we integrate with x. Now, if you look at it, x appears only here, and the limits for x are already given here, namely x is between 0 and root 4 minus y squared, and then dA. And then my typical advice is just to carry out this without worrying about what d is at this moment. Just compute the first integral. And then look at this d, and then this is just x squared. And then now x is equal to 0 to x is equal to root 4 minus y squared, and dA. And then this is equal to double integral 4 minus y squared dA. Then now we got the double integral. Then find out what d is. And then for this case now, if you could visualize the picture of this solid, like I said, d is going to be the shadow. But in this case, it's a little bit difficult to actually visualize this just by looking at the set notation. In this case, just use the set notation to find out what d is. So d is in terms of y and z. So variable x is gone. It has already disappeared. So it's like d is equal to d is a set of all points yz on the yz plane where this is still there. Now, we have already taken care of this guy. So what you're left with is this one. Z, y. Okay. Now, what's this? Well, you have to read off what this region is by looking at the set notation. You have to get used to this. So this is on the yz plane. So d is on the yz plane, where y is between 0 and 1. And then now z is between 0 and y. Z is equal to y. What is this? This is on the yz plane. It's just a line. like this. And then z is equal to 0 to y. So the region D is this one, and this line is y is equal to z. Okay, so therefore, this integral 4 minus y squared dA is, okay, let's just compute this double integral. Well, now for double integral, you fix one of the variables and then vary the other variable. And in this case, you could do either way, but probably simpler way of doing this is this one. So for each fixed y, your z value varies from 0 to, well, y is equal to 0, z is equal to y, sorry. Z is equal to y. So this one is for each fixed y, you integrate with z from 0 to y, and then the y, and the y is from 0 to 1. And indeed, to find the limits for y, what you have to do is basically look at the shadow of this region when you actually light up from the above. In this case, shadow is this line. But anyhow, and then this is equal to 0, 1, 4 minus y squared z, and z is from 0 to y, and then this is equal to 0, 1, 4 minus y squared and y dy. And then if you work this out, you get 7 over 4. So that's the answer. Okay. Then now, let me just note. Like I said at the beginning, where did it go? You may integrate with z first. So z is from 0 to y. So you could fix x and y and integrate with z. In this case, our integral 2x dv, this becomes double integral, and then now 2x, then you integrate with z, and z is from what to what? Where is it? Here is it. Z is equal to, z is from 0 to y, so z is from 0 to y, and then you double integrate whatever you're left with, and then this becomes double integral 2xy dA, where d is what? Just do the same as before by looking at the set notation. So this variable z has been taken care of. Not here, sorry, here. This variable z has been taken care of. So whatever you are left with is this. And that is 0, 1, and 0 x root 4 minus y squared. So that's D. And then what is this region D? Well, actually, it looks like this. This one is, the boundary is 4 minus y squared, but this is x squared plus y squared is equal to 4 by taking the square. So this is actually a circle with radius 4, or radius 2, sorry, 2. And then y is between 0 and 1, so it's 1 here. And it turns out that this region D is this here. And then this curve, outer circle is x is equal to root 4 minus y squared. And then for this, you could integrate it now. Then now to compute this double integral, what you do is to fix y and integrate with x, and x is from 0 to this guy, and then y is from 0 to 1. So therefore, this one, 2xy dA is, like I said, for fixed y, x is from 0 to root 4 minus y squared to xy dx, and then dy from 0 to 1. You could do this way. And then you are supposed to get the same answer. What was the answer? 7/4. You are supposed to get the same thing. To verify this is your exercise. So you could do either way. Okay. Now, let's do one more problem for this video. Example. Evaluate triple integral x squared plus z squared square root dv, where E is the solid bounded by y is equal to x squared plus z squared and y is equal to 4. Here's the answer. For this, better to visualize the picture, and it's not too difficult to visualize the solid E. What is this? Well, this is actually paraboloid, and we have seen z is equal to x squared plus y squared. That's a paraboloid which looks like this, the rotated parabola. And the same, but the axis is different. So y is equal to x squared is on the xy plane. It's like a parabola like this, right? At the same time, y is equal to z squared. It's a parabola which looks like this. So it's a rotated parabola around the y-axis. Namely, this one looks like this. Rotated parabola. And then y is equal to 4. It's just a plane vertically to the y-axis. So this is y coordinate is 4 here. And then, so this surface is y is equal to x squared plus z squared. Rotated parabola. Like this. So in this case, basically this is a solid sandwiched by the paraboloid and the plane. So you better to fix x and z and integrate with y. Fix x and z and integrate with y. With y. So the given triple integral is double integral, and then now y is from here, the lower limit is the bottom surface, so to speak, that's this, and then upper limit is 4, and then root x squared plus z squared, and then dy. And then you do like this. And what's this? This one is, let me write here, double integral, and then root x squared plus d squared. X and z are considered as constant. So this is just a constant, viewed as a constant. And then y is from x squared plus z squared, and y is equal to 4, and dA. And then this is written as x squared plus z squared, and 4 minus x squared minus z squared dA. I'm sorry, this is square root. Okay, and then we have to figure out what d is. But d is the shadow or the projection. Or what I call shadow of E onto xz plane. What is that? Well, that's just a disk. If you just project this down, if you look at the shadow, it's just a disk. So, disk with radius what? Well, when y is equal to 4, so you equate those, you get x squared plus z squared is equal to 4. So it's the circle or disk, to be precise, with radius 2. yz or xz. Radius 2, negative 2, negative 2. Like this. Okay, so this is our z. And this boundary is x squared plus z squared is equal to 4. Okay, then now we have to double integrate this over this region. And since we see we have a disk, when you double integrate this kind of region, what we use is the polar coordinates. But in this case, we have x and z. So x is equal to r cosine theta, and z is equal to r sine theta. And then dA is r dr d theta. Don't forget this little r here. R dr d theta. And then for the polar coordinates, we often see an expression like squared plus squared. That's r squared. So in this case, x squared plus z squared is equal to r squared. And you may just consider this as part of the formula for polar coordinates. And since this is a disk with radius 2, and it's everything in the disk, so the radius is between 0 and 2, everything, so to speak. And theta is from 2 pi. Okay, so therefore, this double integral is written as 0 to 0, 2 pi. And square plus squared becomes r squared. So this is a root r squared 4 minus r squared times r dr d theta. And so this is equal to 0 to pi, 0 to, and root r squared is r, and then you have r, so you get r squared, and if you distribute it inside the parentheses, this is 4r squared minus r to the power 4 dr d theta. Okay, and then now once you get to this, everything is mechanical, and you are supposed to get 128 over 15 times pi. Okay, so that's the final answer. Okay, so this is the end of the second video for this section. And in the next video, I'm going to work out even more examples for triple integrals.